Hello, my name is Pablo Paredes, one of the senior authors of Unstress, Combining Human Factors and Biosignals, led by Yasser and Matthew Mauriello, in collaboration with multiple researchers from different departments and different universities in a truly multidisciplinary effort. Daily stress affects 40% of all days, contributing to psychological distress and exacerbating physical health conditions. Chronic stress stemming from repeated daily stress poses a significant health risk and challenges quality of life. The lack of stable technologies and scalable technologies for timely stress detection hampers the design effectiveness of stress management interventions. Wearable sensors offer a promising avenue for continuous psychological and physiological monitoring and biochemical data collection. Human factors alongside these biosignals are crucial for effective design, enhancing adoption and adherence. During this presentation, you will briefly hear the wearable engineering design factors for a stress sensor e-skin wearable. You will hear about our main research objective about combining human factors and biosignals research, starting with investigating healthy users' reactions to e-skin wearable prototypes and combining human factors and biosignal data to inform future design. You will also hear our main contributions, which are a multidisciplinary approach to combine user-centric and biosignal data to generate a visualization and weighting approach for balanced design and biosignal measurement. And we will discuss how to extend this methodology beyond stress management for broader health and wearable sensor applications. We believe that the integration of human-centric design and biosignal data is crucial for the development of effective e-skin wearables in stress management to foster adoption and enhance overall well-being. The design factors for e-skin wearable start first as understanding that this is a potential emerging solution for stress management. They offer certain advantages such as flexibility, privacy, and comfort. They enable novel metrics like cortisol levels directly related to stress to be tracked, facilitating personalized stress management solutions. We envision 5 different factors. First, make it skin-like and imperceptible using novel flexible electronics. Second, make it private and to safeguard sensitive data. Third, make it multi-sensory, collecting necessary physiological biosignals such as skin conductance, heart rate variability, and cortisol levels. Fourth, make it personalized, tailored to each individual and use case. And finally, make it low cost and disposable to ensure ease of use and reliability. Our main contribution is the ability to combine human factors and biosignals. We perform 2 types of studies, collecting user preference data from a user study and on-body data to assess the quality of the biosignals at the preferred body locations. Then we weighted both human factors and biosignal qualities to create a combined wear index for different body locations. Visual depiction of the wear location combining user preference data and biosignal data is in addition helpful to help us understand this wearable index. Users prefer discrete wear locations like the upper arm for privacy, despite rich sensing areas like the wrist and forehead preferred by engineers. This weighting mechanism merged human factors and biosignals to identify optimal wear locations. For our human factors data collection, we employed a 2-part design probe using semi-structured interviews at the beginning and then body contour mapping. 24 participants attached a non-working e-skin sensor prototype to preferred body locations and provided feedback. Survey responses and body contour maps and interview transcripts were analyzed thematically and statistically. As observed here on the table, strong preference for discrete locations like upper arms and torso were preferred by participants. Concealability and comfort emerged also as primary decision factors. Some additional qualitative findings showed that people had only prior experience with wearables that were wrist-worn and not with e-skin sensors. They were interested, however, in e-skin wearables for stress monitoring after they were able to experience them, highlighting, nevertheless, some social acceptability concerns. Usability preferences balance personal hygiene, signal continuity, convenience, and cost. Understanding user perceptions, preferences, and concerns regarding e-skin stress sensor placement and adoption is crucial for designing socially acceptable and user-friendly wearable solutions. For our Biosignals data collection, we had a parallel group of 10 volunteers using the active e-skin sensor and attach it to the body with a medical tape in 6 different body locations during 2 minutes in a calm seated position. We collected photophyletismographic and skin conductance data from the wrist, forearm, upper arm, forehead, upper chest, and stomach. Biosignal data was normalized against their maximum value, and we recorded average and variation data. Forehead exhibited the highest signal magnitude, while other locations varied significantly. Reproducibility studies indicated signal reliability across multiple measurements. Here we show some samples of PPG from red and near infrared channels and signals from skin conductance from the 6 locations. Pristine PPG signals were observed on the wrist and forehead and leading to adequate peak detection. Signals on the forearm and upper arm show attenuation but were still usable. Chest and stomach locations showed modulated signals affected by respiration, rendering the data unusable for peak detection. For skin conductance, we show varying percentages across different body locations, with the wrist and forehead showing the higher percentages compared to other locations. Understanding the variation in physiological biosignals across different body locations is essential for optimal placement of wearable sensors, ensuring reliable data collection for health. Cortisol, a stress-correlated molecule, was collected separately because a viable microfluidic solution for the wearable was still under development. 16 volunteers underwent a body temperature manipulation method in a portable dry infrared sauna to induce sweat production. Sweat samples were collected from 5 body locations using dental sponges affixed with waterproof medical dressing. Sweat samples were analyzed utilizing ELISA, a lab method with a high sensitivity and low coefficient of variability. Cortisol concentrations were normalized for each participant, with average values shown for forehead, elbows, and knees. Average normalized cortisol percentages ranged from 59% to 82% across all the locations. Sweat cortisol measurement offers a non-invasive method for assessing stress levels. Utilizing a body temperature manipulation method, sufficient sweat was induced for cortisol analysis, providing valuable insights into stress response across different body locations. It is our expectation that skin-like sensors will in the future be able to also produce enough sweat to generate continuous reading of cortisol. From our collected data, body contour maps were generated from biosignal data interpolation, highlighting signal quality across different body locations. Biosignals were normalized and equally weighted to compound their effects. Human factor data representing user preferences were visualized on a separate body contour map. This data was also normalized, balancing positive and negative responses. The wear index was calculated as a combination of user preference and biosignal data utilizing various weight combinations. Optimal wear locations balancing user privacy and biosignal strength were identified as the upper arm or forearm. In this picture, we can see different combinations of weights that can be correlated to different applications. Well-being or public health applications may prioritize human factors, prioritizing locations near the shoulder, while medical applications like relapse prevention for substance abuse addicts may prioritize measurement precision near the wrist. Balancing user preference and biosignal data, the upper arm or forearm emerges as the optimal sensing location for e-skin wearables, offering adequate biosignal strength and user privacy. Flexible weighing mechanisms and visualizations support communication across design and engineering teams. Furthermore, designing for human preferred locations stimulates innovative engineering solutions. An intrinsic limitation of our work has to do with the combination of research practices from HCI, chemical engineering, and psychophysiology, each with different cohort sizes and methods, which makes interpreting data across disciplines challenging. Novelty effects, acquiescence bias, and prior experience with wearables demand that we also think about larger cohort studies as we move forward. Adaptation of weighing based on specific population preferences is also recommended. Preliminary data geared towards wellness and well-being may not be directly applicable to non-healthy populations, and further studies for mental health are recommended. With this, we conclude on stress, a wear index and visualization combining human factors and biosignals. As stated, there's a growing demand for wearables that can monitor stress continuously in everyday life. Combining human factors with biosignals, stress measurement, is essential to design imperceptible and seamless e-skin wearables. Our system offers adaptability to different use cases, allowing for a balance between user preferences and engineering requirements in wearable design. Thank you to everyone, and thank you to all our participating institutions: Stanford, USC, University of Delaware, University of Maryland, Southern Illinois University, and Toyota Research Institute.